Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics, and we have been seeing what are called defects of images. In the earlier lectures, we are continuing the same, and this particular area, namely defects of images, forms the unit 1 of one of the papers coming under basic physics 2, intended for the 4th semester, and we have seen so far the aberrations which are produced by spherical mirrors and also due to spherical lenses. Both mirrors and lenses, they lead to defects, and the defects are primarily due to the aperture, as I told you, and the contents of the lecture number 4 are as follows. We have been talking about spherical aberration in lenses, and in this lecture we will try to see how the aberration produced by spherical lenses can be minimized. And so, we start with minimization or minimizing aberration using stops, and again lens with different radii of curvatures. You can have a single lens. By changing the radii of curvatures or 2 surfaces, the spherical aberration can be minimized, and a condition to be satisfied by the lens with regard to the radii of curvatures. Then the 2 plano convex lenses, when they are separated by a distance d, how the spherical aberration can be minimized. So, the whole of today's talk is intended to see how the spherical aberration can be minimized, and you should remember all these aberrations I am talking about. Is it a spherical aberration or chromatic aberration, which you are going to see in the next lecture, or distortion or astigmatism, all these defects which are produced by mirrors of large apertures and lenses with large apertures, these defects cannot be totally removed, is an important point. The defects will be present, the image that you actually obtain will not be the exact the shape of the object, the image that you have will have some defect, and the degree of the defect can be reduced. So, that is the reason why we talk of minimization and not complete removal of a defect. The defect cannot be completely removed, it can be only minimized. That is the important point to be remembered. So, the cause for the aberration, as I told you, is due to the fact that nature will not obey the man made rules. The man makes a rule like this, 1 by u plus 1 by v is equal to 1 by f, whereas I told you u is the distance between the object and the lens, and as you see from the picture, the distance is this much, right, but you are actually measuring the distance up to this, right. You have u here from here to here, but actually u should be end with the mirror is here, right, but you go up to this point, but light ray is incident here or here, right. You see the light rays incident on at this point and this point, but you are measuring the distance up to this point, right. V is the distance measured from the image plane to this point, and this excess distances, right, that you have got here, right, when you are talking about u also you should end up. So, with the mirror, but it goes beyond the thing, and this error can be minimized if you have got light rays, only paraxial light rays, right. The light rays are very close to the optic axis, these errors will be minimized. That is the reason why we are telling that the curvature or the aperture of the lens should be minimal. So, instead of having a large aperture, if you have got a mirror only of this much dimension, right, then you will be having only the paraxial light rays. The marginal light rays will be absent. This is the marginal light ray. The hitting at the peripheral region, right, that is the marginal ray. As I told you in the last lecture, you know, these are marginal ray. Okay, they are the marginal rays, whereas that gives rise to a focus here. IM is the focus due to the marginal rays, whereas IP is the focus obtained here due to the paraxial rays. The light rays which are passing through that zone of the lens closer to the optic axis, right. These optic axis, these the blue colored light rays come to your focus here, right. This image is very clear. The image that I show here, it does not have any defect. These blue rays, they are the paraxial rays. They come to your focus here, that is IP, whereas the red colored lines that I have drawn here are the marginal light rays, because they are hitting at the margin or the end points of the lens, very close to the edge of the lens. So, they come to a focus at this point, right. This is the marginal ray focus, the paraxial ray focus. These two foci are different, and the best possible image is obtained here, and that is the best image that you get here is called the circle of least confusion. The image that you obtain here is called the circle of least confusion, that is the best possible image that you can obtain. Okay. This is what I told you now so far in the last lecture, and so you have the man made relation is the simple equations derived connecting the object and image distances, right. This is what I showed you here, the object distance and the image distance and the focal length, they are the man made relation, right. The focal length are based on assumption that the angles made by the rays of light with the axis are small, and paraxial approximation may be made. What do you mean by paraxial approximation may be made? If the light rays are very close to the optic axis, then the distance that you are measuring, V will be ending on the mirror, right, not like this. V is measured from here to here, right. You draw some triangles and compare the heights as you do in the high school. You draw some the light rays passing through the some point it is incident, and then it is getting reflected. Okay, the light ray in a mirror, it is reflected here, and another light ray is passing through this thing, and you look at this triangle, and okay, you compare the two triangles and then obtain the relation, right. This is what you would have done in the high school, but the point is when you take the distances u and v, you are going up to this point, this plane, but whereas the mirror ends here. And so, the man made approximations will not be made by nature. That is the reason why the light rays, the paraxial light rays only will come to a proper focus. Otherwise, you will have two foci, one is the focus obtained due to the marginal ray, the other is the paraxial ray, that leads to the spherical aberration in the case of lenses that we saw. Now, whatever spherical aberration that we have come across, we have been seeing so far produced by a lens can be minimized by what is called a spherical lens. Now, a spherical lens, you see the light rays here, they are the light rays, this is the optic axis, right. this is the optic axis, the best focus point is here, right, best focus point, and this lens with this kind of shape, you see the difference in shape. It is not a spherical lens, right, it is a spherical lens, that will lead to best focus as is shown in this picture. Okay, that is called a spherical lens. That is a possible way by which it can be, the aberration can be minimized. Now, all the optical instruments, they make use of concave mirrors, the telescopes, binoculars and microscopes, all of them, because the light rays either are reflected or transmitted through the, or refracted and transmitted through the lens. Now, these light rays will lead to invariably the various defects. So, mirrors and lenses cause various kinds of aberrations, hence the images obtained will be found with defects in all the optical instruments. Okay. Now, I will be now discussing the various methodologies which can be obtained to reduce the aberration, to minimize the aberrations, but not, I am not going to completely eliminate, the elimination is impossible, only you can minimize or reduce the spherical aberration or chromatic aberration or whatever aberration you are talking about. So, the aperture that you have got here, you got the lens, the light rays are cut, right, the, you place what you call a stop, there are the stops. What is the function of the stops? They cut the light ray which will be incident on the margin of the lens. This light ray will come and hit at the lens somewhere here. So, by placing stops, what you do is the marginal light rays are cut off. As I told you earlier, the paraxial approximation, the light rays which are incident on the mirror or on the lens, those light rays which are parallel to the optic axis, the so called paraxial rays, that will lead to only one focus. So, by cutting the marginal rays, you are allowing only the paraxial rays, right, only you are allowing the paraxial ray, right, the paraxial rays, only the paraxial rays are allowed, and they give rise to a better image. A better image can be obtained by cutting either the marginal rays or the paraxial rays, both can be done. Either you cut the paraxial rays by putting the stops, you can have stops here and allow the marginal rays. If you allow the marginal rays, the focus will be obtained here. Okay. If you allow the paraxial rays, the image will be obtained here, but in either case the image will have a better quality. So, the aperture in this case, what happens is the aperture blocks out rays that blur the image. The advantage is however a greatly reduced light throughput of the lens. By cutting the light rays, what you do? The intensity of the image that you obtain will be lost, because partially you are cutting the light rays. Okay. The intensity will be lost, but the quality of the image will be better. So, you can use stops. So, one method of reducing spherical aberration using what are called stops. By stops, what we mean is we are stopping the marginal light rays being incident on the lens. Okay. By cutting the marginal light rays, you allow only the paraxial light rays to pass through the spherical lens. That will lead to a better image, but the intensity will be somewhat poorer, because you are cutting the some of the light rays are being cut. So, by using what are called stops, the image quality can be improved. This is one of the methods, right. I will go to other methods later, but once again I show this is animation which can be you can adjust this and make a prime. The mirror is here and you have two focal points. I am talking about a spherical mirror. I am from spherical lens, I am coming to spherical mirror back. Now, you have got the light rays which are the marginal light rays will come to a focus here, the paraxial light rays will come to a focus here. So, there will be two focal points leading to a blurred image. Image is produced will be blurred. So, the perfect image can be obtained by changing the shape of the mirror as I show here. So, this can be the animation which can be you can change the position, the curvature can be changed from spherical mirror. If you go to a parabolic mirror, then the spherical aberration can be removed. So, as I told you, the spherical aberration can be reduced by using what are called stops. Spherical aberration can be minimized by using stops. The above reduces the effective lens aperture. The stop is used to permit either the axial rays, the paraxial rays, or the marginal rays of light. In this picture, which one is stopped? Using stops, you are cutting the marginal light rays. You can also place the stops here to cut the paraxial rays, right, allowing only the marginal rays. That is what I am showing here. So, the stop is used either to permit the paraxial rays or the marginal rays. So, you will be getting a better quality, but with a reduced intensity. Hence, the amount of light passing through the lens is reduced because you are cutting some portion of the light. The image will be less brighter, that is what you will be getting. So, we will go through some amount of mathematics because of the fact that we are going to change the spherical lens of more or less having radii of curvature R1 R2. The radii of curvature R1 R2 will not be very much differing, but now we are going to have a lens which will reduce to the maximum extent the spherical aberration, and we will see under what condition the spherical aberration in a convex mirror can be minimized to the maximum extent. So, the condition is to be obtained. The longitudinal spherical aberration, what do you mean by longitudinal spherical aberration? That is the distance that separates IM and IP. I showed you earlier what I mean by IM and IP. IM is the image obtained at you have IM here and IP here, right. The focus IM due to marginal rays and IP is due to the paraxial rays, right. I want to reduce the distance between IM and IP. This is called the longitudinal spherical aberration. The distance that separates the two foci, one is the marginal ray focus and the other is the paraxial ray focus. Now, the distance that separates these two foci is called the longitudinal spherical aberration. Now, this has to be reduced, right. Okay. That is what I am planning to do by using a lens which will have differing radii of curvatures. Differing radii of curvatures, by this what I mean is the R1 and R2, they are the radii of curvatures. There will be enormous difference between R1 and R2, that you will see now. So, the longitudinal spherical aberration produced by a thin lens for a parallel incident beam is given by an expression of this kind. So, x is the longitudinal spherical aberration. I showed you just now, your IM is here, IP is here, the distance separating IM and IP is called x, that is called the longitudinal spherical aberration. That can be given by an expression of this kind, that you see on the right hand side. The longitudinal spherical aberration x is equal to rho square by f square into k square times mu square plus k into mu is the refractive index, mu plus 2 mu square plus 2 mu cube plus mu cube minus 2 mu square minus 2 divided by 2 times mu into mu minus 1 whole square into 1 minus k whole square. So, your k is I will come to k later. K is the ratio between R1 and R2 is k. Now, x is the longitudinal spherical aberration for which you have got an expression of this kind on the right hand side, and rho is the F2 is the second principal focal length, radius of the lens aperture, f2 is the second principal focal length, and as I told you, k is nothing but ratio between R1 and R2, where R1 and R2 are the radii of curvatures of the lens. I am going to have a lens, I am going to prepare a lens wherein the R1 or R2 will differ by a large extent. The purpose of doing this is to minimize the spherical aberration, and I have to now obtain a condition what will be the value of k, or how much R1 should be different from R2, what should be the difference between R1 and R2. So, I want to reduce this dx, right, dx with respect to your k. So, I want to reduce dx. So, I want to make dx by dk equal to 0. I want to reduce dx by dk equal to 0, right. Dx is what? X is the longitudinal spherical aberration. If dx by dk is 0 means I am making Im to coincide with IP, the two foci to come to the same focus. For a given value of mu, which is the lens f2 and rho, the condition for minimum spherical aberration is dx by dk is equal to 0. So, differentiating the above equation, right, you have got the equation for x, right, you differentiate this x with respect to k. By differentiating x with respect to k, what will be obtaining the following: k will be equal to R1 by R2, that is how you define k. That will be a function of simply the refractive index. So, that will be mu times 2 mu minus 1 minus 4 by mu into 2 mu plus 1. Okay. So, k now you should remember it is a function of only the refractive index. So, by having a flint glass prism or some other material, okay, the prism is made up of some material having a particular refractive index. It may be made up of crown glass or a flint glass. So, depending upon the value of mu, let us assume mu to be equal to 1.5. Let us see what happens to k. Let us assume from the above equation, for a lens whose material has a refractive index mu is 1.5. What is the refractive index of water? It is 1.33, okay, refractive index of water. What is the refractive index of glass? In general, the refractive index of glass is 1.5, but you should also remember, as I will be doing chromatic aberration, mu is a function of what? Function of wavelength. Mu is a function of, so mu, the refractive index is different for different colors. I will be talking to you later about mu v, the refractive index for the violet ray, and mu r, the refractive index for the red ray, because all of you know, you would have done the experiment for finding the dispersive power omega, that is given in terms of mu v and mu r. That shows that the refractive index differs for different colors, but now I am not talking about all these things. For now I am having mu is equal to 1.5. So, if I put mu equal to 1.5 in this, what will happen is my k will be equal to minus 1 by 6. Okay. Your point is substitute here, in a place of mu is substitute 1.5, k will come out to be minus 1.6. What does it mean? What is k? K is R1 by R2. Now, R1 by R2 should be equal to minus 1 by 6. Let us not worry about the sign. So, if your R1 by R2 is equal to 1 by 6, that means R2 should be 6 times R1, or okay, whatever be the thing you can call R1 R2. So, the radius of curvature of one surface should be 6 times larger compared to the other surface. Okay. The radius of curvature of this is 6 times larger than this. So, the lens will be of this shape, it will be almost plane. The curvature is nothing but, radius of curvature is nothing but the mirror forms or the lens forms a part of a sphere. Okay. From center to the lens is the your R1, and so I have got a lens here another surface like this. So, I have got a lens almost plane, perfectly more or less plane, and here it is more curved, right. So, you got two surfaces, one having a radius of curvature R1, the other R2, but whereas R1 will be 6 times that of R2. So, the conclusion that you obtain from this kind of mathematical relation that you got here, if mu is 1.5, then you produce a lens such that you have a biconvex lens such that the radius of curvature of the surface facing the incident light is 1/6 of the radius of curvature of the other face. So, one of the faces should be having its radius of curvature 6 times larger than that of the other surface. So, you have got two surfaces having two different radii of curvatures. Two different means enormously different, that is 6 times the radius of curvature will be 6 times larger compared to that of the other surface. So, a lens for which R1 by R2 is equal to minus 1 by 6 is called a cross lens. The deviation produced by the two surfaces is the same, and hence the rays of light are made to come to a focus with minimum spherical aberration. The spherical aberration can be minimized now in the case of a lens if I have the curvatures, radii curvatures of the two lenses, if they differ by a factor of 6. But it should be noted that the spherical aberration, as I told you earlier, cannot be completely eliminated in a lens. In any lens, the spherical aberration cannot be completely eliminated. The spherical aberration produced by mirrors, the spherical aberration produced by lenses or chromatic aberrations, all other aberrations can never be eliminated, they can only be minimized. The images that you obtain, the quality can be improved. Now, you see the lens I have been talking about, wherein you find the radii of curvatures are differing by 6 times. Now, we will pass on to the summary part of the lecture. The spherical aberration can be minimized, as I told you, using stops. The other possible method is it can also be minimized by using a proper lens having different radii of curvatures. The condition for this lens will be for a lens for which R1 by R2 is 1 by 6, the aberration will be a minimum. Let us now have the following questions. The question 1, how do you minimize spherical aberration? Question number 2, comment on the radii of curvatures of a spherical lens which will lead to a minimum aberration. The last question is whether a spherical aberration produced by mirrors and lenses can be completely eliminated. With this, we come to the end of the lecture number 4, and the rest of the things with regard to the defects of images we will see in the lectures to come. Thank you.